So, hello and welcome everybody to our most recent edition of Rust Linz. So, it's already the 28th meetup. It's again a late night edition. We do that once a year when Rainer is totally into the advent of code, working every day on the newest examples. And I try to get my kids to sleep and then run a meetup. It also allows us to invite people from outside of Europe who live in different time zones. And this is something that I really, really enjoy. So I'm really happy to invite a couple of guests today to talk with us about Rust. Before that, a couple of things that we usually do. First of all, this meetup is brought to you by the Coding Club Linz. The Coding Club Linz is doing a lot of great events all around programming and coding in and around Linz. Those are, there's an autoplay. I didn't know that. Okay, this is going to be fun. Today's speakers are Carl Cady, who is already here, who is going to tell us about 9 rules for creating procedural macros in Rust. I'm really looking forward to that one. That was a really exciting proposal. And then we're going to see Vitaly Bragilevsky, I hope I didn't butcher his name, who works with JetBrains, and he will talk to us about profiling code in Rust. I'm sorry for all the autoplay here. I don't know how to turn it off, but that's okay. So if you want to interact with us, you can do that on YouTube. A chat is open there for you to ask questions during the show. I'm going to collect them and answer them and ask them afterwards. Or you join us on Discord. We are a lovely community of beginners that exchange about Rust, so you feel free to join us there as well. I'm going to post a link to Discord in just a second. There are a couple of community news. So the Coder Linz is the prime event of the Coding Club Linz. It's a programming club for kids from age 8 to 17. The next online meeting is happening. Oh, that's tomorrow. So check out linz.coder.net for more information. Next, we have our friends from Female Coders. So if you identify as a woman, you can join them on January 11. So that's next year for some new study groups. Also, the mother of all meetups from Linz is back again, January 26. We meet again. We don't have any talks yet scheduled. They are coming in the next couple of weeks, but we are at an exciting new host. Everything about that is on Technology Plauschality. And one thing more, oops, there we go. So this autoplay is kind of annoying. There will be a tech workshop day on January 13. Game hacking with Rust. I guess this is in the Grow Garage with the support of Cloudflight. Check it out at oxa.at. And that's the end of the presentation already. So I'm fighting an autoplay here. But hey, if anybody can tell me how to turn it off, I'm prepared for the next time. But yeah, so those have been all our news so far. I'm going to share them with you on Discord so that you can check on them later. And with that, I like to welcome our first guest on stage. So with a click of a button, I want to welcome Carl. Good
Hello.
Day, Carl. How's it going?
Very good.
So usually we ask people from where in the world you are calling in, but I guess looking at your surroundings, I also have to ask you from what time are you calling in? So what time is it in your area?
Yes, I live in the Seattle area, which should be rainy probably today, but I'm visiting my son in Los Angeles. So this is 1 o'clock in the afternoon, 1 hour afternoon in Los Angeles, and it's a sunny day.
Oh, fantastic.
Maybe 12 degrees Celsius today.
Oh, well, amazing. So it's also 12 degrees Celsius here in Linz, but below zero. So we have one of the coldest winters in the last 5 years or so. It's snowy outside. It's icy, so it's I love that weather. Once a year, that's cool, but I guess it's totally different. So that's amazing. So yeah, this is what I like, that we can welcome people from all over the world, and I'm really looking forward to your talk. So I'd say I put on the slides, I remove myself from the stream, and I want to give you a warm welcome on our stage. This is Carl. Please enjoy Carl's talk, 9 rules about procedural macros in Rust.
Thank you. So I'm going to talk about creating procedural macros in Rust. These are lessons I learned when I created a Rust macro for myself, maybe of interest to other people, called any input. And we'll use that macro as an example. We'll talk about it more, but it's basically to make it easier to write functions that can be permissive in what kind of inputs they allow. I don't know how to advance to the next slide.
There, you can do that in the on the screen directly. So if you hover over
I see it
the
now.
streaming screen,
Okay.
you see buttons there. Yeah, cool.
I got it. Thank you. So by way of introduction, 11 years ago, I was working as a developer at Microsoft Research in the Seattle area. And we created a genomics package called FastLim that we open sourced. That was written in mostly Python with some of the performance pieces written in C++. 3 years ago, I retired and began work as an open source volunteer, continuing to maintain the FastLim project. Most of that work involved things like updating the Python from version 2 to version 3 and just kind of keeping up with some user feature requests. 2 years ago, I finally just became fed up with maintaining the C++ part of the code and replaced it with Rust. And that was successful for the project. And it also led to an article called 9 Rules for Writing Python Extensions in Rust. Last summer, I pulled out a piece of the genomics package that reads a particular genomics format called BED and made that available. It was already written in Rust, but it wasn't easy to use from Rust. It was made to be easy to use from Python. And I wanted to see if I could make an API in Rust that was as good as what I was able to make available in Python. I think I was. It was more work to do it in Rust, but I think for users, it's just as usable as Python. And that became an article called 9 Rules for Elegant Rust Library APIs. Finally, this fall, I simplified the Rust code with this new any input macro. And along with this talk, you can get all the details from an article on medium.com, specifically towards data science, called 9 Rules for Creating Procedural Macros in Rust. So let's talk about the any input macro that I wanted to create. And I'll start with a question that everybody can kind of ask themselves. If you were writing Rust and I ask you to write a function that accepted any kind of string-like thing, would you know how to do that? In other words, instead of just taking a stir or a string, you could do it borrowed or moved. There's also references to strings that can be borrowed. Could you make a function that could take any kind of string? So your user wouldn't have to match your kind of string. I bet I can kind of remember how to do that. So that's not the hardest thing in the world to do in Rust. But what if I asked you to do the next thing, which was to write a function that it could accept as input any iterator-like thing, where each component of the iterator was any path-like thing? It's getting more complicated. I'm sure some people can do it. I'd have to look this up every time I would do it. And then the final challenge here is, what if you're using the multidimensional array package, ND-array, but you want to accept a normal Rust vector of F32s? Would you know how to have a function that could take a vector of F32s, but inside your function, it would look like an ND one-dimensional array view? And I didn't even know that was possible for most of the time. The point of this macro is to make that easy. And we can look at an example on the left. Starting at line 3, we can define a function that uses this macro. We say pound any input. We define a function called length +2. It has an input called s, which is of type. It's not a real type. It's our special type called any string. and it returns a U size. And then inside our function, we just say s dot length plus 2. That's what our function does. And you may not believe that this can take any kind of string, but you can see starting lines 10 through 18, I'm passing in strings, strs, references to strings, and sometimes they're borrowed and sometimes they're moved. So that demonstrates what the macro can do for strings. And on the right side, we've got a more complicated example. Now we'll say we want to define a function called toItersum. Its first input is called iter1. Iter1 is any kind of iterator of U size. And iterator2 is any iterator of any string-like thing. And the function returns a U size. And then inside the function, we're going to sum up the numbers we get in the first iterator. And in the second iterator, we'll take the length of all the string-like things and we'll add that to our accumulating sum, and then we'll output it. And at line 13 on the right, you can see an example. We call toItersum on an interesting iterator, an iterator where we're iterating from 1 to 10 inclusive, and then also an array of strings or strs or something like that. And that works fine. And we can call the function, it'll return the correct answer, which in this case is 61. So that's what the macro I wanted to create and have created does. So how do we create a macro like that? The simplest kind of Rust macro is called a declarative macro. With that, you use the macro rules macro to create your macro. When you can use it, this is the right thing to use. It's simple to use, easy to read, but not as powerful as I needed for this project. The other kind of macro are procedural macros. There's 3 specific kinds, but they're all very similar with respect to how you program them. So there's function-like macros, derived macros, and attribute macros. The attribute macro is the one we'll be using. That's where, like on the top of a function, you can say pound square bracket and the name of your macro, and that'll cause your macro to be called. On all these procedural macros, what happens is you write your code one way, and before the compiler actually compiles your code, it sends a token string of the code that you wrote into a function. That's the main thing you're going to have to write. Your function is going to return a token string, whatever that is. We'll see that in a bit. That you can think of it as your original thing expanded or modified, transformed some way. And then that second thing, after it's run through your macro function, will be what the compiler actually compiles. So I could have called this talk 9 suggestions for making procedural macros, but if you call something just suggestions, it's kind of boring. So I'm going to call them rules, but that doesn't mean that I'm really the authority on this and that you have to do everything I say. There really are suggestions, but I think it's just less wishy-washy for me to be a little bolder and call them rules. So we're going to look at the rest of the talk will be 1 slide per rule for the 9 rules. 4 of the rules will relate to syntax trees, how to convert among the various types related to syntax, how to learn about the syntax tree data structures that you'll need to work with, how to construct new syntax trees for your output, and when you need to recursively manipulate syntax trees, how to do that in a way that's not too terrible. There'll also be 5 rules related to other topics, including how to develop your project your macro project as a non-macro project. It sounds a little strange, but it turns out that makes things much easier. How to create unit tests that you can actually debug, how to do error handling, how to do integration tests, including UI tests, and the importance of following the rules of just general elegant Rust API design. So turning to our first rule, the first rule is that you should develop a procedural macro as a normal non-macro project. That means your project will actually have 3 projects. There'll be a top-level project. It'll be very small. Most of it will just be your documentation. The only important part of it is to re-export a function that's defined in the next level project. So in this case, the next level project, which I'm calling the derive project, defines something called any input underscore derive any input, and that in the top level project doing that pub use any input derive any input means that our top level users will see that any input function at the top level. There's not much more to the top level than that. So that brings us to our second level project where we actually define the macro. That will be a function that, in this case, any input that takes some token stream input, or in this case, inputs, and returns a token stream. In my code for this level, and I recommend this, I only have 11 lines of code, because what's really going on is I define this function any input, and all it does is call any input underscore core, passes the 2 inputs to it, and then takes the output from any input core and returns it. And you'll notice some intos. That's because there's actually 2 kinds of token streams that are designed to be very similar and interconvertible, and doing those .intos tells the compiler that it can convert them for us. So we've had 2 levels that have done almost nothing. The core project is where the real work gets done. We define a function. In this case, I called it any input core. It takes some inputs of type token string and returns a token string. Now we'll actually write a bunch of code that'll do the conversion of the code that we want. So the user will give us, in the any input case, a function, and we'll see this in a bit, and then we'll return the modified function. And we can have lots of other code for helper functions and all kinds of data structures and unit testing. So you may think it's confusing to have 3 Rust projects when you really only wanted to write 1. Anytime you do macros, you're always going to have 2. The top 2 I have here. I strongly recommend adding the third, because it makes debugging much easier. It allows you, because the core project, the bottom one, is a non-macro project, you can do things like set breakpoints. I use VS Code. So you can set a point in your code, in VS Code, a breakpoint runs line by line, single line at a time, look at your variables, just all the normal stuff you would do with coding becomes available at this lower level core project. It's not available at the derive project, and that's why we keep the derive project so small. One help with having to have a thing that you think of as 1 project be 3 projects is Rust has a feature called workspaces, where you can tell it that these 3 projects are coordinated and work together. And if you read the article, it'll talk about how to set it up, these 3, as a single Rust workspace. And so that means the overhead of having 3 projects isn't too bad. So rule 2 is we want to create a procedural macro, you need to be able to freely convert between token streams, syntax trees, strings, and literal code. And we haven't defined token streams, and we don't know what syntax trees are, and I guess we know what strings are. Let me give an example. So look at line 5 that This is a first implementation of the any input function at our core level. It has the first input args of type token string. We're not going to use that input. The second input is called input. It's of type token string. That'll be a tokenized version of the user's, in this case, function. And we're going to take that, and at line 6, we're going to call the parse2 function and tell it that we'd like it to convert the token stream called input into a syntax tree object called item fn, item function. And that'll be called old item, be assigned to a variable, old item function. Then we're going to put that old item function into a function called transform function, which you can see at line 11. Transform function will take an item function, do some things, and then return an item function. Specifically, the first thing it will do is print whatever the item function is. And we can do that with print line and this quote macro with that pound sign. It's kind of a little magic syntax. But if we do that, which we do as a debugging, like during development while we're developing, if the user passed in a function called hello universe, print hello universe, you can see it down below in the white, it would print the string hello universe, function hello universe, print hello universe. We can also see this item function thing as what it is, and it's a piece of the syntax tree. All the syntax tree is a nested structure of structs and enums that are defined in a crate called syn, S-Y-N. So if we told it to print the syntax tree, it would start by printing what you see in the lower line of the white, item function, and you can see that's a struct, and the struct has an attribute called ATTRS, which is an empty list or array, and it has a field called viz, which has some value inherited. We'll see how we can learn what these are. It has something called signature, and so on. So looking back at let's look at line 14 in the function. We've printed out the user's function in syntax tree form to strings. We're going to return a bit of code, and the code we're going to return, no matter what, in this first version, no matter what the user passed to us, we're going to return the function hello world that does a print line hello world. And the way we do that is, you can see lines 15, 16, and 17 are that function. And by putting them in the parse quote, which you can see at line 14, that's a way that to capture literal code, which is lines 15, 16, and 17, and turning it into an item function. And it knows which item function because it knows the return type of transform function. Anyway, think of it this way. There's these 4 kinds of things: token streams, strings, syntax trees, and literal code. And we might want to convert between any of them. There's functions to convert every which way you'd want. They're a little bit hard to figure out, a little bit hard to remember, but you're in luck because I made a table. So here's my, on the right, you can see my table of 16 combinations of things that you might want to convert to and from, and what the exact Rust syntax is to do them. So this is in the article. I'd recommend keeping this at hand. I was using it all the time. So from rule 2, we now hopefully have some ability to convert among all the types that we have to deal with. We want to start, we'll say we're going to start in kind of a test-driven manner. So we want to create debuggable unit tests. And let's look at an example of what one of those would look like. This is just in our lowest level core project. We define a test, just like a normal Rust test. This one's called one input. And the first thing we do in lines 65 through 68 is we show what a user's input might look like before we apply our macro. So the user might have something called any string length that takes as input S of the pseudo type any string and returns a U size. So we call that before. We also, starting in line 71, show it what we expect the function to be converted, what do we expect our macro to convert this function into. So you can see it's still a function called any stir line, but now it's got a generic type called any string 0. And that's now the type of our input, the actual type. And there's a where clause that says that any string 0 is specifically an asref stir. And also line 76, you can see that we expect that the macro will add a new line. It'll say s equals s dot asref. And then after that, the rest of the code should stay the same as it was before. So we have our before code, our expected code. At line 81, we just pass in our before code to our main core function. Mine's called any input core, and get the after code. That'll return token strings. And then we can just assert that the token strings we expected, the ones are expected, are the same as the ones that we actually got in after. And any tokens EQ is a little function I created. You can get it from GitHub or from the article. All it does is make sure that the two things are equal. And if they're not equal, it does a line diff to help you figure out where something went wrong. And then finally, on these unit tests, I usually take another copy of the after code and just run it on something. So here I'm taking any string length and applying it to the string ABC and verifying that it equals 3. And that's just to make sure that this thing is doing about what we want. The nice thing about putting this in the core, the lowest level project, is again, we can set breakpoints. So if something isn't working, we can set a breakpoint at line 82 and then, line 81, where we call any input 1, any input core, and we can actually watch the code. We can go into the code and watch it execute line by line, look at variables, and that makes debugging much, much easier. So one of the hardest things about writing procedural macros is that there is this huge number of enums and structs that are used in the syntax tree format. And it's not immediately obvious how to learn how to use them. So here's my recommendation. Take a function that you're curious about, for example, what's in the black rectangle at the top, and then go to AST Explorer, which is a website, Abstract Syntax Tree Explorer. Make sure you set it to Rust. When I first went there, I only saw the JavaScript version, and I got very confused. But there is a Rust option there. You can paste your little function into AST Explorer, and it will output what's in the gray box on the left. In this case, we can see that it sees a file and some things, and then an item fn. And we think, oh, maybe the Rust syntax tree representation for a function is an item fn. What's an item fn? Well, it looks like it's a struct with 3 fields, attrs, viz, sig, and block. Sig itself is of type signature. Signature is some kind of struct with a bunch of inputs. So that gives you just some clue that you're, in my case, that I'm interested in the syntax tree struct types of like item, FN, and signature. When you know those, you can go to the documentation for the syn crate and just look them up. And you can go and say, oh yes, item FN does represent functions and it does have these 4 fields. And now you've got kind of a hook to let you get in and understand what you need to understand on the code that you actually have. This also gives you an opportunity to use kind of the normal Rust destructure and pattern matching to access parts of the struct or the enum, parts of your syntax tree. For example, in my code, there's a situation where the function that the user gave me may or may not already have a where clause. If it does have a where clause, I need it to return it to me. And if it doesn't have the where clause, I need to create an empty version of the contents of the where clause. So you can see line 3 on the right side that I take the item FN input and say .sig, that gets me to a particular field, .generics gets me to a subfield, .where clause gets me to another subfield, and then do Rust pattern matching to see if that where clause is actually there. And if it is, I pull out one of its parts called predicate. And if it's not, I use the parse quote that we saw from rule 2 to create an empty, basically an empty predicate structure, which is you can see the return type line 2. It's something called a punctuated where clause comma. And again, we know that because we've used the AST Explorer to find out what types were expected. So now we have at least a handle on passing in the user's thing, in my case, a function, knowing how to converting it into a syntax tree, being able to see what kind of structs and enums we expect the syntax tree to contain. We might get to a point where we want to actually generate some new code that's different from the user's old code. The simplest way to do that, and should definitely be done when it works for you, is to use the parse quote macro. And another important way that's not too hard is with Rust's update syntax. So first, the parse quote. In my macro, I need to create a line of code. It will be the first statement, and it'll become the first statement in the user's function. We saw the case where I had S was an any string, and I wanted it to say S equals S, let S equal S dot asref. So on line 1, we're passing in an identifier. In the scenario I'm talking about, it would be S, the variable, input, the variable, the letter the user is using for input. And you can see lines 4, 5, and 6 is where it generates this new statement that's going to become S equals S dot asref. And you can see it's got this kind of substitution syntax with the pound sign that actually makes it pretty fun to use. In the case of iterators, we still generate a statement, but it's a little bit different. It would be like iterator 1, let iterator 1 equal iterator 1 dot into iterator. And in the case of my multidimensional arrays, it's yet another line that we would want to add. But in all the cases, it's the parse quote makes it pretty fun to generate new code, and we can put in our own, we can substitute in our own values. The other straightforward way of generating code is when you want to generate a new struct. So on the right side, I want to generate a new item function. So I say, okay, I want a new item function. The first field is sig, and then I've got some expression that tells how I want to set that field. The second field is block, and I have got some expression to say how to set that field. It's got 2 more fields. I don't want to change them. I want them to be exactly what they were before. So just standard Rust feature is that you can, when you're filling in a struct, you can say ... some other structure that's the same type, in this case clone, and it'll just fill in the last two fields of my new item function that it's creating with whatever values it had from old FN. It's at line 12. If you've only got 4 fields, then maybe it's not that important. I could have just specified all 4. But if we look at line, I think line 3, signature, I'm creating a new struct of type signature. I set the generics field to something that I know I want it to be. I set the inputs field to be what I want it to be. And then I say the rest of the fields should just be the same as they were before. That's line 6. And this saves me a lot of typing because I think signature has 9 fields. So this was just a nice standard Rust way of creating new structures based on old structures and not having to specify every single field explicitly. Let's go on to the next. So it would be nice if we could do all our programming destructing and constructing our structs and enums with the methods I've said so far, but it doesn't work because some of these structures get really complicated because they can be very recursive. So for example, we've seen things where our user might have said, had a function with an input S is any string. Okay, that's not that complicated. They could also say V is a vect of any path. It's like, okay, that's a little more complicated. Now our special pseudotype is inside a standard type vect. Or we could have A is an any array of any path. So now we've got 2 of our pseudotypes nested. It's getting more complicated. Even worse, say they have a variable called yikes, and it's a pseudotype special, I'll say pseudotype, any iter where each element is a vec, where each element of the vect is any array, where each element of the array is any path. And you can just look at that and see that you're going to have to use recursion to handle cases like this. So the good news is the syncrate provides a nice mechanism for doing all the recursion that we need for both visiting and creating, manipulating syntax trees recursively. It's all attached to the fold crate. The way it works is you tell it to start recursively processing some syntax tree, and then for all the types that you want to do something special with, and it knows there are 187 syntax tree structs and types. The ones you care about, you tell it to do something special for those types. The ones you don't tell it about, it'll do nothing as a default. Sometimes when you're doing the recursion, your type, in my case, something you want to manipulate, might itself be built to have subparts that are also something you want to manipulate. So you have to do recursion within recursion, nested types. It can still handle that, but you have to be careful that you set that up the right way or you'll miss the inner one. And that's too complicated to explain now, but look at the article. It's not too bad. It's just a special line that you have to put at the right place. Okay, that was all. I think that's all the programming, inner programming syntax tree stuff. So let's talk about error handling. Rule 7 is use the proc macro error crate. All Rust code needs to handle errors, of course. Sadly, macros don't use the Rust result types that we're used to in regular coding. We know that we don't use results. We can often just call panic, which isn't as good as results, but is something. That kind of works with macros, but not perfectly, because when we return an error message in a macro, we want to be able to point to the part of the user's code that caused the error. We want a location. And if we call panic, like we would in normal code, it won't have the location information. One moment. There are a couple efforts to improve this situation, but within proper formal official Rust, but they're either in nightly and they don't seem to be working their way out very quickly, or they only work as on your top level function. They aren't something that you could call when you're recursed 4 levels deep, parsing the user's code. So the good news is someone has created a third-party crate called proc macro error, and it does exactly what we want. It's just like panic, except we say abort and we can give a location. The downside to it is that it brings in some overhead and makes it slower. I think it's more than worth it because it does exactly what we want. And it's also trying to be compatible with the way that things might officially get standardized. So you'll only have to make little changes going forward if the error handling in macros story matures. So here's an example. Inside my macros code, I check to see whether the user, when I have nested pseudotypes, they should be using the angle bracket. So like any iter of any string should have an angled bracket. If the user does a round bracket, I will detect that in this function at the top, and I just call abort. Span range is something that I was able to easily bring in from the user's code to say which code caused the problem, and I just return a string. When the user actually calls the macro, they'll get this nice underline. You see at line 5 showing where the problem was, and a nice error message, expected angled bracket generic parameter. So I'm really happy that this macro, that this third-party crate exists, because it makes things very sensible. Rule 8 is do integration testing, including UI testing, specifically with try-build. Everything we did for testing so far was down at the lowest core level. We were calling our function that the macro calls, but we weren't really seeing what happens when the real compiler calls our macro before doing its compilation. To do that kind of testing, you have to do it at the topmost level, and you should do that. Here's an example. This is just a top level test. We have a test called oneinput. It has a function inside it where we define any string length, with s being of my pseudotype any string, and it just returns the length, and we just assert that the any string length of 1, 2, 3 in quotes is equal to 3. So that's a very nice integration test. The compiler is really running the macro, and everything is good there. The only problem is, along with testing that it works well, we also need to test that when the user makes a mistake, that it's giving the right error messages. And to do that, we create a test we'll call UI tests that use the try-build crate. The way the try-build crate works, and people use it for other things too, is you create little bits of Rust code in a directory, like a UI directory shown on the lower line 4. So like test1.rs, test2.rs, whatever you want. The try-build will find your files, run them through the compiler, expect them to fail, check that the standard error strings produced by the failure are what you expect. And if they are what you expect, then the test passes. And if they're different than what you expect, the test fails. The way it knows what to expect, the first time you can let it run, they'll all it won't know what to expect, but it'll output what standard error it actually saw. And if you can look at that, and if you like it, you can put it in the right directory. And then from then on, it'll check that it is consistently creating the same error messages when that it should be creating. All this testing at multiple levels seems complicated, but if you set things up with the workspace mechanism I mentioned before, then you can run all your low-level unit tests and all your integration tests just by saying cargo test __ workspace. Okay, our final rule. The final rule is to follow the rules of elegant Rust API design. That had 9 more rules. The 3 most important ones, though, are to use Clippy, which is the linter that checks that you're kind of doing things nice. You got your capitalization of variables right and all that. You should make sure you write good documentation, because you're designing something for other people to use. And if you can't explain how to use it, then maybe your design isn't good. And you should test your design on your own projects, what we call eating your own dog food. So I had 2 Rust crates that I tested this on, the any input macro in. I have one called fetch data, which downloads and caches big sample files from the internet. It's compatible with Python's popular pooch package. That was just so when a user gave me a path of something, it could be a string or a path or a reference to a path. That worked fine, but that was a very simple case. The more complicated case was bedreader, where I actually had iterators of strings and things like that. And when I first did it, I was surprised, because when I looked at the documentation that bedreader generates, it turns out that for all these procedural macros, the documentation uses the version of the functions or data structures after the macro has run. So I had a function in bedreader called chromosome that passed in an iterator of any kind of string, but the documentation actually shows the generic types that the macro generates. And the first time I did this, I was using types like T0, T1, and that was hard for the user to read and might conflict with their own generic types. And then I did big, long, random types, so there wouldn't be any chance of conflict, and that became too hard to read. And so I ended up with this, where I created generic types like any string 1, any iterator, any string 0, any iterator 1, which seemed like I'm satisfied with this design. And the reason I found it is because I actually applied my macro to a real project and got to exercise it. Okay, so this is my last slide. The conclusion is, if you follow these 9 rules, you can make writing macros as easy as writing regular Rust programs. Regular Rust programs that manipulate large nested structures. So it's kind of easy, but still not super easy. The plus is that with procedural macros, you can do almost anything. Many of us love Rust. If there's anything you think could be better, you can actually make it better yourself. If there's any redundancy you see in your own code, just because of your project, you have a chance to remove that redundancy to make the language more productive for you. The minus is that some things seem hard when you're creating procedural macros: debugging, testing, error handling, understanding syntax trees. I think all those are made easier if you follow these rules, which require you just set things up right, and things do get easier and become easy under these rules. And it really does allow you to unleash your productivity. So that's the end of the presentation. Thank you.
Thank you very much, Carl. Thank you so much for your presentation. So, wow, cool. That was a lot of great stuff. We have one question from the chat. I don't know if it's in any way related, but I show it anyway. I guess we can both answer it.
Sure.
For UTF 1F9B8, so that the semantics are right. when they apply derive annotation to their struct, it's not analogous to a C++ inheritance. Yeah, I guess
I think that's correct. It really is good to think of all these procedural macros as you're writing this macro code that just takes the function or the struct or whatever it was the user wrote, you're feeding it through your code, you're returning a new bunch of token strings, which is probably a new struct, new function, whatever, and that gets sent to the compiler. So I don't know that you couldn't use derive to do something analogous to C++, but that's not the way that it's probably good to think about it.
Yeah. There have been also a couple of comments on Discord regarding the error issue from Zishan. Hi, Zishan. Nice to see you. The error issue is not relevant if not using recursion. Of course, recursive is way cleaner. Do you have any comment on that? I'm going to.
Can you say that again?
I'm going to put it on in the chat. Give me a second. There it is. So this was the comment. The error issue is not relevant if not using recursion, by the way.
I don't know. So if you know that you can catch every possible error at the very top level, then you don't have to use this third-party package. But even if you're calling your function that calls your function that calls your function, not 12 levels down, but just 4 levels down, no recursion, there's no way the only place you're allowed to put a nice error message on the current standard without having to use a third-party package right now is at the very top level. So I think for almost every use case, unless it's very simple, you're still going to want to do something like this. Or if you know the user's errors are simple enough, you don't need the underscore thing, then you could just use panic, and that's okay for now. Hopefully in a few years things will be better.
Cool. Then we have a couple of other comments which are all related to, can we put the material of your talk into the YouTube description once we publish it on YouTube? I guess we can. So
yes.
Maybe either make it out from the video, or I'm going to ask if you can provide me some links. And then
I'll give you the slides, and the article is on Medium, but it's set to be free forever. So the article is always going to be readable.
Fantastic. That's great. And with that, Carl, thank you very much. This was a really exciting talk. So I rarely did any things in macros. So I dabbled a little bit with them, but I usually didn't have the use cases for that. But I'm actually really interested in giving it a spin and trying it out. So it's good to have this guideline, to have a couple of steps to keep in mind. And I think this is going to be my next project. So there you
go. It was fun. It was really fun.
Thank you. So thank you so much, dear chat, dear viewers on YouTube. Please give us a round of virtual applause. They're coming. That's fantastic.
Thank you.
That, Carl, thank you for being with us. Good greetings to your family. Greetings to Los Angeles. Enjoy the nice weather.
Auf Wiedersehen.
Auf Wiedersehen. Ciao, ciao. Bye bye. Alrighty. Oh, and I'm sorry, UTF-1F9B8. There was the last question. I'm sorry. I'm going to answer it afterwards. Don't worry. I want to welcome our next speaker. Vitaly is here. So, hi, Vitaly. It's Vitaly Dragilevsky. Is that correct? Did I say that right?
Well, I usually say Vitaly, but that's fine.
Okay.
I think.
Okay. So one quick question. So I hear a little noise in your microphone. Would you mind checking real quick if the settings are all right? It's a little, the usual noisy stuff that you get from some microphone shenanigans.
So I don't know. It said right microphone. Maybe.
Oh, now it sounds much better.
Okay. Good.
Okay. Did you do anything?
Yes. I actually.
Okay.
I've disabled echo cancellation.
Okay. Now it sounds really nice. So perfect.
Okay.
So really fine. Fantastic. Cool. So hi, Vitaly. Great to have you. Where are you tuning in from?
Well, I'm in Cyprus right now.
Oh, cool.
It was 20 degrees today.
Oh,
Now it's night, but yeah, it was 20 degrees.
wow. Oh, that's
Yeah, not
I'm not sure,
minus,
but
not minus.
yeah, I'm not sure, but I think I'm jealous. I
Yeah,
love
I
the cold
know.
weather, seriously, I do. But oh boy, being in the sun now would be nice as well. Alrighty, so Vitaly, we are going to hear from you about profiling code in Rust. I'm really looking forward to this presentation. So Vitaly just sent a proposal through our Sessionize website, just I guess about a week ago or something, and it immediately caught my eye. Like, okay, I really want to see that because I always talk about profiling and debugging. Honestly, I rarely do it. So that might be really, really interesting for me. So it's totally selfish. I'm totally selfish in getting this talk now on stage. So without further ado, Vitali, now I have it.
Yes.
The stage is yours. Welcome to Rust Linz and have fun.
Yeah, thank you. Thank you, Stefan. Uh, yeah, so I'm going to talk about profiling code in Rust, and my name is really Vitaly Bragilevsky, and I work at JetBrains, and we at JetBrains, we love Rust very much. And I will use Lion for doing this presentation. It's our main IDE for writing Rust code. But in fact, the things that I'm going to discuss here, they are a little bit more general than doing Rust with our Rust plugin in Lion. And Stefan said a very important thing, that he doesn't do profiling. And I would like to start with the results of some survey which was held like a year ago. But this survey is actually very, very disappointing. So we've asked, what profiling tools do you use for Rust? And it turned out that 84% don't use profiling tools at all. And this is very, very disappointing. And in this talk, I would like to discuss this situation. Why is it like that? So how can we do better? Do we really need that profiling? So this is what I'm going to discuss. It's actually a very simple talk. So I will give you several advices, but they're very simple and you can apply them and your code will be better and you don't have to work hard to do all that stuff. So, but profiling tools are not very popular among Rust developers. So let's discuss why. So maybe all those people, they just don't know what is profiling. So let's start with discussing definition. So if you look at Wikipedia, you will see a definition of profiling. So Wikipedia says that, and I will show you this definition part by part because every word there is very important. So we have to understand it clearly. So Wikipedia starts with this disclaimer. So we're going to discuss profiling in software engineering because, well, in real life we have some other meaning of profiling, but in software engineering it's a little bit special. First, profiling is a form of dynamic program analysis. You may know that there is static program analysis and dynamic program analysis. And static is done during compilation, and dynamic is what we do during runtime. So we run our program and we do some analysis. So we analyze some program behavior at runtime. So this is what is profiling. Then this dynamic analysis measures something. This is also important. So program analysis can do checks. For example, in Python, they have dynamic type checking. So they check types at runtime. So it's not measurement, but profiling measures. So we want to find out some characteristics of that runtime behavior. So what are we going to measure? For example, we measure space or memory usage, how much memory is used by our program. Then time complexity of a program, so how much time does it take to run that program. The usage of particular instructions, this is also important, how many times we read this and that. And finally, the frequency and duration of function calls. So this is what Wikipedia says. So we analyze runtime behavior of our programs in terms of memory usage, time, usage of instructions, and some characteristics of function calls. So this is profiling. Now, why we don't profile? And Stefan doesn't profile, and as he confessed, and all those survey participants don't profile. Why?
Vitaly, sorry to interrupt you real quick.
Yeah.
We are getting feedback from the microphone again. I don't know if anything has changed, but it's now really noisy again.
No.
So I'm sorry to interrupt you here.
I think nothing changed. Maybe okay. Let me try to change microphone. Maybe. So what about now?
It sounds a little, like you're in a room, which you maybe are, but so not that nice. But at least we don't have any noise and feedback. So maybe we shall continue with that if that's okay for you.
Yeah, it's okay. It's okay.
Cool.
Okay,
sorry, and
sorry
thank you
that.
for letting me interrupt you.
Yeah, no problem. Yeah, thank you. All right. So why? We can think about several reasons, actually. So reason one, it's really hard. Or people say that it's hard. Maybe that's not the case. Maybe sometimes it's easy, but we don't know about that. And reason two is that it's not necessary at this time. So people say, well, we don't need to profile it right now because it's not a problem. So our programs are efficient enough, so it's just not necessary to do that now. And then they also say, so there are some very, very smart folks in our team, and in that team, so they'll do that when it's necessary. So like we have a team of 10 people and one of them is just doing profiling all the time. But if we postpone that profiling, then just imagine how many things should be fixed. If it's like we develop our program for a year and then we just start profiling. Isn't that a big problem? And then there is also another reason. Some people say that they don't want to do premature optimization. And you may know that this is a famous quote from Donald Knuth, that premature optimization is the root of all evil. So you may have heard about that. So here's Donald Knuth, and this is this quote. So premature optimization is the root of all evil. But as it is usually the case with some funny quotes, the real meaning of that quote is a little bit different. Because if we read it full quote, then we'll see that Donald Knuth doesn't ban premature optimization. So what he actually says, or he wrote in one of his papers. So he wrote that the real problem is that programmers have spent far too much time worrying about efficiency in the wrong places and at the wrong times. And then this premature optimization is the root of all evil. So premature doesn't mean that we do it too early. Premature means, in his quote, that we don't do profiling first. So it's not about banning profiling, like doing something to optimize our program. No. Donald Knuth suggests the real path. So first, we profile our programs, and second, we do optimization. And this is what we're going to discuss in this talk. So how to profile, how to find which places are right places to do optimization. So that's what we're going to do here. All right. To present some ways of profiling, I will use some small project. So I solved lead code problem number 22. I will describe it in a second, and using several methods. And then I just use this project as an example for doing profiling. So this problem is about generating well-formed parentheses combinations. Like we have opening parentheses, closing parentheses, and we put them together just to make it well-formed. So, for example, if we have 3 pairs of parentheses, then here you can see the output. We have 5 possible well-formed combinations here. And in my project, I have 3 implementations. One is breadth first search, second one is depth first search, and sub-combinations. There is an information about that in the README file. If you look there, you can see what's going on. All right, so this is linked to the GitHub, and we'll explore this project right now, and we'll see what can we do about that. Okay, so if you are interested, here is the QR code and link to this project. So let's see it. And remember, I'm in CLion, so I will use everything here. So to present this project. So first, let's look at the project structure. So of course, we have some source files here, and I have 3 implementations. They are all I put them in separate modules. We have main file, we have library, so just as usual, library crate, binary crate, and all those implementations are in there. So we also have benchmarks here. We'll talk about them a little bit later. We have Docker file. I will show you why I need Docker file here. We have tests, of course, integration tests here. So this is our project structure. Quite usual Rust project, nothing special. We can run this project. So let me run it here. So first, I can run it using command line. For example, cargo run, and here is it. So I need to provide some arguments. There is some help. I can do that here. So a lot of information. So to run it, we need to provide the following. So I want, for example, to be verbose, and the size of the problem will be 12. Here is it, 12. And then I'm interested in breadth first search implementation. So like this. So if I run it, I will see some information. So if I don't want to write all those arguments, I also have some run configurations in the project. So I can run them like here, for example, run BFS. Here is it, breadth first search. So I don't need to provide arguments all the time. I just saved it in run configuration. Here is some results. And of course, I have tests, and I can run tests. So here is it. Everything is all right. So we're on the safe side. And whenever we change something, we can test again just to see that we don't break anything. All right. So this is small project overview. And now let's get to the main stuff. So what does it mean to profile memory usage? Here are several questions that we may be interested in. For example, how much memory is taken by some containers, some string or a vector or stuff like that. How much memory our program uses in total? So when and how we allocate memory, because memory allocation is some operation which requires working with the operating system. We have to do system calls. It takes a lot of time. So we want to know for sure when that memory is allocated. So is it deallocated correctly? Like people often say that we don't have memory leaks in Rust, and this is definitely not true. It's possible if you use reference counting, something like that, it's possible to get some problems. So there are several simple things then that we can do in this regard. So how we can profile that. So I'm going to present them, but remember, I'm not going to talk about something very sophisticated, not at all. So no sophisticated things, but we can do a lot using just very simple stuff. So let me show you some examples of the code, how we do stuff. So I will start with this. So let me just sort something. I will change some structure of my IDE here. So just to see everything, and I'll get back to presentation mode. So here we are. So our first tool is just asking for length and capacity of our data structures. For example, here you can see some information about memory usage in our program. So I just ask for the length of the vector, just as usual, and the capacity of the vector. So length is the number of elements in that vector, and capacity is the memory usage. So how much elements we can put into vector without changing its size. So very simple, but it's actually very helpful. So I think I can show how when we run it. So here you can see the size and capacity are just the same. All right, very simple. And we can do the same with strings, for example, string capacity. We can check that too. And so I computed here. So here is a problem with strings. And we know that if we have 12 parents, that means 12 pairs of parentheses. That means that the size of the string should be 24. But average capacity per string is 38. And that means that a lot of strings just use more memory that we actually need. So even if we look at such a simple characteristics, then we'll see that there are some problems. Like 30% of memory isn't actually used for good. So a little bit of problem. Okay, then let's look here. So what is this function, dynamic usage? Usually vector doesn't have such a function. It comes from another crate. So I will show it here. It's from memuse. So if you add this dependency, you will get this function which tries to do its best to compute the overall memory usage of your data structure, such as vector or hash map. You can use this dynamic usage function with everything. So just add this library and you can get a lot of new information. And I also use human bytes here, just to present this information in this nice way. So you just see like 7.6 megabytes and stuff like that. Oh, by the way, it's a little bit outdated. I can update it right now. Maybe it's better. Yeah, hopefully nothing will break here. Let's write check as usual. As we do that, we write tests all the time, and if it's fine, then okay, we are on the safe side. So just nice. Okay, so we can use very simple library to check memory usage, like this dynamic usage, and just we can get a lot of information about that. So how many memory is actually used by our programs. But these are very simple things. Let's use something more sophisticated. Namely, let's do real profiling. So I will use instruments. So I'm using macOS here. And in macOS, there is this program, Instruments, that actually shows you a lot of information about your program. So it's profiler for macOS operating system. So let me call it. So here I run a program with BFS and DFS one after another. And then I want to see how the memory is allocated. So I'm talking about memory allocation here. So let me run it. And it runs the program. It compiles all the information. And when it's over, it shows us how some information in a graphical way. Here is it. Here we are. So this is BFS, and you can see these steps, how memory is getting bigger and bigger. Like this allocation, then more allocations, even more allocations here. If we look at this graph, we can see, for example, that there is no memory leaks here, because this is our first BFS algorithm, and then almost every memory is freed, and then we start our second algorithm, and then again we do a lot of allocations, and then everything is freed again. So this behavior is actually very good. One possible problem that we can see from this graph is that we do a lot of allocations here. So we can see it's some stats here, but it doesn't matter for this moment. So when we do a lot of allocations, and you see these steps here, you can think about time which is spent on that allocation. So every time we ask operating system to give us more memory, maybe it's better to ask for that memory in advance. Then we'll ask it for just once, and then it will be this graph will be a little bit different. All right, so I will close it now. So very simple thing. In fact, if you are interested in this instruments library, you can use it with Cargo. There is a create Cargo instruments. You install it, and it's just some intermediate thing between instruments and your Cargo project. But of course, not everyone has macOS. Like in Windows, you have Visual Studio Profiler. Well, it's totally different, but the idea is the same. So you don't need to know a lot of things about your program to see this small graph. It's very easy. So many people have Linux, and in Linux, we have the main tool for doing profilings is Valgrind. So let's run Valgrind here. So I have special run configuration for Valgrind, and I use Docker to run it because, well, we have Valgrind for macOS, but it's not supported in a very good way. So let's run it in a Docker. So I have Docker container. I'll discuss it in a minute. Let me write run terminal here. and in terminal, I go to the directory with this project. I do cargo build, and while it's updating crates, let's look at this Docker file. So Docker file is actually very simple. It's Ubuntu, and I install Valgrind, some Clang, C compiler, something very, very essential in order to make all this workable. And then I also install Rust, and I use stable Rust. And so very simple Docker container. And I use here Docker integration for Selenium, and it's installed. You don't need to install it because it's bundled with Selenium from the very beginning. So with this Docker file, we can run everything we want in a Docker container. So we have Valgrind and we have Rust, and then let's wait when this build is over. So my idea is to see that we can have the same graphs as in instruments, but for Linux. So we don't have to do something with our operating system. Sometimes profiling in different operating systems shows different results, but that's hard part. But we are talking here about easy parts. So for us, if it's okay in one operating system, then it's okay in another too. All right, so we've built it. So I can run it. So this is my path to the executable. It's target, Docker, it will be debug build. This is from program. So this is it. Yes, this is it. So I will write verbose version with size 12, and this will be BFS. So here is it. It just run it. And now I want to run it using Valgrind. So it's just the same command line, but I add Valgrind. And Valgrind is actually a family of tools. And one tool I want to use here is called Massive. It's memory analyzer. In Valgrind, there are several memory analyzers. So Massive is one of them. So I run it. And while we run it, it creates a file. We can see it here. And it's actually very, very long text file. But fortunately, there is a special program here to analyze it. It's called Massive Print. Okay. So once again, it's a lot of information, but there is something interesting in the very beginning. Let me show it to you. So here is it. This is actually the same sort of a graph we saw in instruments. It's in text form, but still it gives you almost the same information. The behavior can be a little bit different, like the behavior of allocation, because this part depends on the actual operating system. They have different allocators and different system calls and stuff like that, but still it just allocates something and then it's freed everything up. So this is the behavior of our program, and we can use it very easily, and we can see what's going on here. So in order to profile memory usage, yes, and we can see the amount of number of bytes allocated and stuff like that. So we can see these pictures, and if we change something, we can compare with those pictures and see if something is different. All right, now let's look at time profiling. Once again, very simple things. We want to know how much time does it take to compute results. And we also want to know where the program spent most time. And that means which functions are hot. So these two questions are actually the same thing. Hot means we spent a lot of time there. So how we can do that? The first, very simple thing. We just use standard time functions from Rust. For example, here, I check time in the beginning, and then I run algorithm, and then I see how much time is elapsed. So that's it. Very simple. So let's run it. Run it again. So for example, this one. So it's just this information got result in this timing. So in many cases that's enough. So I just mark the beginning, mark the end, and see how much time was elapsed at this algorithm. Sometimes it should be a little bit more interesting. For example, we can do benchmarking. And while doing benchmarking, let me show you my benchmarks. I use a criterion library here. So I will run it. Benchmarking, for example, this breadth first search. And what is actually going on here? Criterion runs our functions many times, like 100 of times. And then it computes some statistical characteristics. For example, here we can see this is average time we run it. And so this is for different sizes. Like if n equals to 5, then we have this 2 microseconds. And for n equals 2, we have 1 millisecond, and then 16 milliseconds for n equals to 12. So we can think about these stats. So we just benchmark them, and we can remember. And if we change something in our program, we can benchmark again and see what changed. So this is profiling time. So now we know that our functions take this amount of time for these sizes. We can also do profiling with a special tool here. So let me run profiler. So I use the same run configuration, but now, no, not that. But now I will ask for profiler. Here is it. And what we see here, it's so-called flame graph. And this flame graph is extremely important, and it's extremely important to understand what's going on. So this is all our program, like in time. And this is generate parentheses function. Like it takes 63% of the parent of this, almost all our program. So most of the time is spent at this function. But if we look further, we'll see that the problem is that most of the time is used for reserve for push operation. And this is something that goes from vectors, Rust vectors. So why, instead of generating parentheses, instead of solving our problem, what we actually do is we reserve memory. And then we also do some reallocations. And then we allocate new memory. So most of the time, like 66%, is taken for vector operations. And this is definitely a very bad thing. So we don't want to spend time on memory allocation. And if you remember all those steps and now in our instruments graph or Valgrind graph, that's exactly because of this behavior. So we look there, we looked here, and we see that we have a problem in our software, in our code. So we've done profiling, and we see that a lot of time we spent on allocations, and this is not a very good thing. So we need to do something about that. Okay, what can we do about that? Several very simple techniques I want to share with you. Like, I'm sure everyone knows about them, but they're so simple. So sometimes we just don't do that. But they're not only simple, but they're also very powerful. So I'm not going to take your time writing code. So I will just show you what I already have. Actually, we are here, and I have several commits in another branch just to show you what's going on. So how to change that. And our first practice is to reserve memory in advance. So we use capacity for that. So instead of allocating memory when it's needed, we reserve it in advance, and then we reduce the number of allocations. For example, let's look here. Oops, not this one. I will need it here. Okay, let me again restructure these. No, sorry. I want to exit presentation mode to change a little bit this. Okay, here, this will be better. Right. So, fixing capacity. So before we had creating just new string, but in fact we know the exact size of the string. Like if it's 12 pairs of parentheses, then we'll have 24 symbols, characters in our string. So we know the capacity. So instead of doing new, we say string with capacity, and we create string with exactly this capacity. So just reserving memory in advance. Very simple technique, but it's actually very powerful. And if we do that, there will be no excess memory usage inside strings. And we have a lot of strings, because you can imagine, like hundreds of thousands of them. Then we can do the same with vectors. Like here, I was creating just empty vector, and I push stuff to that. But it turns out that in our algorithm, I can compute the future number of elements in that vector. And if I computed them, I can spend some time on computing. Doesn't matter what I'm actually doing, but I'm trying to predict the number of elements. And then once again, I use for vector this with capacity function. So I create a vector of the specified capacity, and then I reduce number of allocations. So this is first very powerful but very simple technique. Then we can do resizing. Instead of reserving capacity, we can create new elements just in the very beginning. Those elements will be empty, and then using mutation, we can put the right values there. So for example, I'm doing in the next commit, like resize in advance. So how we can do that? Where are our changes? Like instead of having a vector, now I have a mutable iterator, and instead of putting elements to the vector, I use that iterator to put things there. So I've created a large vector, and all the elements are already there. So I'm not pushing those elements. I have them already, but those elements are empty. So I just mutate their values. For example, here there is an element, this combination, and I put new line. So I change line inside that combination. So I mutate that. Okay, and here I create new vector, and then I resize. And then I put these are my new elements. They will be empty, but the size will be correct. And then I'll change those elements. Here is it. My next technique is avoiding temporary structures. It's not always possible to avoid because borrow checking can make it hard to do that. But still, when it's possible, it's a good idea to do that. So, for example, here, before I had a new vector, and now I just remove it. I don't have a new vector. Instead, I use the same vector and I resize it to be able to get all those new elements. So I go over first part of this vector and I put elements in the second part of that vector. So you know, in Rust, it's difficult to mutate several parts of vectors, like beginning and end. So it's not that easy. So here I use very nice function split at mute, which gives you two parts of vector, and both of them are mutable. So you can just do, so old part of the vector is first half, new part of the vector is second part, and you mutate something in the first part, and then you can mutate something in the second part, and during one loop. So very powerful, and you don't need a new vector anymore. And once again, you reduce number of allocations. So really, really very powerful. And one other technique here, like it turns out that we don't need all those memory reservations at all, because we know exactly how much parentheses will be in this problem size, because it's so-called Catalan number, and we can compute them. So if you have this function, doesn't matter what is it, but it gives us this size. So instead of pushing, instead of resizing, we just say, well, total capacity will be this one. And then there will be no allocations at all. And of course, whenever we do these changes, we have to check if everything is all right. So whenever we do all those optimization techniques, we have to test. So for now, let me check out this optimized version. Okay, here we are. And then, of course, I'll run tests. So this is optimized version. Okay. And now let me see what's going on in our instruments. So what's going on with our memory? Okay, we're on this program. Okay, and this is it. Okay, do you remember all those steps that we had before? And now there are almost no steps. Like we reserve as much memory as possible. We've reduced allocation, and this program behavior is much, much better. So real difference. Okay, and if we, of course, we can also run our profiler. Okay, run VFS with profiler. And let's see. This is our generate parentheses function. And before we had a lot of memory reservation stuff here, and now we don't have it. We've just removed it. Okay, what about timing? Is it any better than before? Maybe it's not better. Let's try our benchmarks. Here is our benchmarks. We compile it again, we run benchmarks, And criteria library is so powerful, it shows us how much better our program, our implementation is. Okay, now it's improved 55% better. It's for smaller size and for another size also improved. And for the last time, I think it will be improved too. Yes. So everything is improved. So Criterion just is able to compare it with the previous runs. So you see that I've showed you very simple things, very traditional Rust things. But if you do profiling at early stages, you just see all that stuff. And it's really, really very powerful. Well, of course, it's still hard. So I think I don't need all those windows. So we'll get back to my slides. So it's hard, but there are many tools, and I've showed you Valgrind family. I've showed you instruments. If you are interested, you can look at this library, DHAD-RS, which was designed specifically for Rust, and it allows you to introduce profiler into your program. You just add several lines, and then you have a lot of possibilities. It's also very, very powerful. So it's difficult to know all those tools, but it's a good idea to at least to get familiar with some of them. If you use Linux tools, they're mostly terminal-based. So you just run them and you see all those huge files. There are visualizers, you can look at them. But one important thing is that you don't have to understand everything in those files. Well, it's just not necessary. Instead, you just try to look at important parts, and that's enough for many cases. If you look at tutorials, then usually they focus on hard things. But it's not necessary to know all those hard things. In fact, in most cases, you don't need that. So I've showed you a couple of graphs, and then it's clearly visible that we have a problem. And then we've applied some simple techniques, and now it's clearly visible that we don't have that problem anymore. So you don't need to apply very sophisticated instruments, very sophisticated techniques to make your programs better. So that's important idea. As usual, for doing 80% things, you just need to master those instruments at 20%. No traditional Pareto rules. So it's hard, but you don't need all that. So I want you to start profiling as early as possible. Don't postpone it. Don't delegate it to other professionals, because it's easy and it allows you to write better programs. And that's it for this talk. So you can download these slides. Here is the link, and feel free to talk to me in Twitter and whatever. And thank you very much.
Thank you very much, Vitali. Thank you so much for your talk. First of all, having your slides in your IDE, nice. So that was quite a surprise when you suddenly pulled out your project structure. That was really, really good. We actually have a couple of questions here. Some discussion questions, some others as well. So the chat is booming right now. That's fantastic. Let's start with so one nice comment from Crypto Unit that was really nice, like, well, the Rust folks are not using profiling tools because using Rust is actually going for max performance and optimization. Yeah, of course, but this led to a very interesting question by Hans Peter. Hi, Hans Peter. Where he thought it would be interesting if there's a difference between Rust and C++ developers. So if you know from your statistics, the 84%, if that's Rust developers, if that's C++ developers as well, or if you know if there's a difference in their behavior.
C++ developers profile more, but not much more. As far as I remember, difference is not very big. So, but still, so we know that our profilers are not very popular among developers. So maybe I think the reasons are just the same for C++ and for us, and that is very unfortunate. I think people think that it's very hard, so they don't try to do that. So. Yeah, no matter what language they use.
I totally agree. So I can see the same things, for example, in JavaScript, where it's still considered somehow a dark and mysterious art that folks, that just super experts are going to use, where in reality, it's you open up the right tools and then you can start interpreting, and you just need to cross that barrier to actually get started.
Exactly.
So I think this is why your talk is really important also for folks who are working Rust, so that they can see, well, this is approachable. This is something that they can actually do. Another question by Juraj, last speaker from last time. Hi, nice to see you again. So is profiling only available for Rust on desktop server, or is it also possible to use CLion for profiling Rust apps on embedded devices?
Well, support for embedded devices is a little bit problematic at the moment, but we work at that. So we are trying. So there is this thing like remote debugging, and we are working to make it more accessible and easier for Rust embedded developers.
Cool. Then we have a few more questions from UTF-1F9B8. I hope you get your name right. What's the best, easiest way to enable turning profiling on off so I can collect data from production, or turn them on off for specific modules or functions? Do you recommend any patterns or articles?
Well, that's. I don't remember anything in particular to answer this question. So the create dhat rs that I mentioned during my talk, it does a very nice thing. So it enables tests with profilers. So if you use that create, you can immediately see that during your runtime, your behavior is becoming worse or better, and then you can analyze what's going on. So it's like tests that you have at runtime, and there is quite a good description of that create. So maybe I would advise to look at that, but yeah, nothing else comes into my mind here.
Then UTF-1F9B8 has one more question, which is, do you have some CLion discount for Rust hobbyists, or are you planning Hoppala on community edition?
As far as I know, we don't have plans for launching a community edition of CLion, but yeah, the problem with profiling is that we don't have profiling in IntelliJ IDEA Community Edition. So that's true. That's unfortunate for our users, but well, we still need to have some paid products.
Yeah,
So
I've been in a workshop just recently where usually Ryan and I say, well, if you want to get started and you don't have the tools, start with Visual Studio Code because it's free and it's available and it's good. And almost every developer there had C-Lion with the Rust plugin, which came to a surprise to us. So we haven't seen that yet. So I guess folks really love your product.
well, yeah, that's very good.
There's one more comment from Crypto Uni, I guess, related to the question from UTF-19B8. Now I can say it in my sleep. Maybe I'm mistaken, but profiling is supposed to be done prior to actually deploying it in production, as opposed to, let's say, gathering real-time metrics through observability and monitoring. What's your take on that?
Well, I was talking mainly about profiling, yes, prior to production. But still, it's possible to have it at other stages too.
Okay.
So it's like runtime, production time observability. So you can inject profiling components into that stage too. But of course, it's a little bit more sophisticated because when you do profiling, you have some additional instructions in your code. Well, usually under profilers, your code runs more slow because of those instructions. So there are these downsides, but still it's possible to have profiling code at production too.
That's great. Sorry, I'm just losing my voice here. I don't know why. Just 1 second. I also think so. If you're going to run into production, gathering telemetry from things like OpenTelemetry and etc. is really a really good idea. It also gives you a little bit of overhead, but I guess a different kind of. So yeah, cool. Those were the questions, and it was really a nice discussion on YouTube. This is very interesting. It was a fantastic talk. Thank you very much. As always, we are going to put up the videos in a couple of days on YouTube, so they will be cut, polished, put up with a nice little intro. With that, I want to say for everybody who's still online, please put out your clap emojis and give a round of virtual applause for Vitali. I'm going to pronounce that name correctly now. And with that, thank you very much for being with us. Thank you very much for joining Rust Linz. It has been a pleasure. And yeah, I hope we see each other in the future.
Hope so.
All right. Thank you. And with that, dear friends from Rust Linz, thank you for closing the year with us. It has been a fantastic year. We had some really great talks. We had really, really nice speakers, events. It was a wonderful year. Let's go into 2023. Take care. See you in the next year where we're doing another batch of 12 Rust Linz events, hopefully. So Merry Christmas, Happy New Year. See you around and bye-bye.